My co-conspirators, fellow researchers, they're actually academics. So we have paper in somewhere, and they care about this stuff. The problem, Bogon filters, you're familiar with them. We intend to filter unallocated address space, including 1918, the stuff the IANA hasn't given out, et cetera, in order to protect ourselves from malicious attacks and unwanted traffic, because we believe that there are people out there who send from that space. Over time, this unallocated address space may become allocated, given down from the IANA to the registries, used, announced, etc. And then we see all the winding on the NANOG list and the other operators list saying, I've just been assigned 96, 38, 266, 42, and I can't get to X. So the problem is the filters need to be updated, but they seem often not to be. Now, you think you know why, but there's a hidden secret here. The real cause is that Joel Yeagley has been talking to, guess who? You never knew this.
I never knew this. Yeah.
And this is the root cause. But in typical engineered fashion, instead of dealing with the real problem at layer 9, I'm going to attack it at layer 3 and 4. Okay. So the objective is to develop a methodology that's capable of detecting and locating them. Not just what we've been doing previously is, here's an address you can ping. If you can't get to it, go figure it out, Charlie. It's actually locating it to analyze the reachability status of an allocated prefix, okay, and say where the failures are. For the experiment, Aaron loaned us 3/16s in 3 newly allocated, given down from the IANA, but not yet given to victims, /8s, 4 of them actually, and I think we only experimented in 2 is my memory. Okay, so how do we test the reachability? First, let's define some terminology. There's a test prefix, duh. Okay, there's an anchor prefix. That is a well-established prefix whose reachability should be fine. It's been there since 1948. It seems to send and receive packets successfully. Both of those are announced from a test site. In fact, in both of these, in all of the tests, they were announced from the same machine, behind the same routers, at the same site. So the test prefix might be 96.0.1.1, and the anchor prefix might be 147.28.035. Is that what it says there? Yeah. In fact, those aren't might be's, those are actual examples. Okay? And so the probe site is this rack at the Westin, multi-home site. It's got a machine in it from both those prefixes, connected to the internet. There are 2 classes of probes we're going to do. In probes, those are probes coming from out in the internet, being sent to both of those prefixes, the test and the anchor. They're probes and they're trace routes. Okay? For the in probes, they're trace routes all the way. So you can see here, unfortunately because there's 2 screen stuff, I can't point very well. This kind of works. Okay. So you can see that we expected both of them to go directly, but in fact, due to this stuff, oh my God, and maybe it diverted this way. And I'll go into some boring detail on this in a minute. For the out probes, okay, we go from the test site to a whole mass of IP addresses out there on the internet. And if it fails, then we're going to do the trace route. Okay, so the testing the reachability of a prefix. In other words, hey, can we from out here on the internet reach that prefixes? You've got the anchor and the test IP, and we assume that they're propagated in the same way as they're announced from the same location. In other words, I'm assuming that the announcing probe site the home site for both these prefixes is not doing a different announcement policy outwards of these two prefixes, so that any routing anomalies, any announcement anomalies, are caused by immediate neighbors or the set of ASs out there in the world. It's not that I'm announcing the two of them differently. Okay? So we assume that, and from each trace route server out in the internet, we trace route to the test IP and to the anchor IP. Okay? And you can see obviously what would be expected, and if you have a blockage, i.e. there's either there's a route filter as opposed to a packet filter, you are either going to die if there's no other way to get there, or you will divert to another path. Okay? And for the moment, let's assume that the other path you divert to is less optimal. Okay? How do we get these test sites? Okay? The in probes, well, I'll get that in a minute, I guess. Got to hear more first. The in probes give reachability information towards the test and anchor prefix. Okay? If it diverges, we can start to build a list of candidate ASs who might filter. Okay? And in fact, what we end up with is when we started, we went to try to look at things at AS granularity, and we very quickly learned that broken Bogon filter policies are not AS contiguous. In other words, they're ASs that work partly and don't work partly. So we had to break things down to the router. Okay? The problem with in probes is they catch only filters that are between public traceroute servers or looking glasses, etc., in the test site. And we can only find a limited number of these traceroute servers out on the internet, places from which we can traceroute. We'd love to traceroute from the whole edge. Good luck. Okay? So, and we can only find a limited number of filters because of this, but at least it identifies intermediate AS candidates that we would become suspicious of. And what we did, let's get to the detail, is we advertised the text and anchor prefixes from Iraq and the Weston. Gert Doring did it from Munich. Andy Linton did it from Wellington. And Maz, who's here, did it from Tokyo, in IIJ's network. These networks are very disjoint. We got 480 public traceroute servers and Planet Lab nodes covering 56 countries, okay? Plus, there were some, I forget, a large number of people who volunteered when I put out that posting saying, please run this program that did the traceroute and ping in. Hundreds volunteered from the NANOG posting. So, we categorized them. Good. The anchor and test prefix took exactly the same path. We went down the walk and we couldn't find anything blocking it. 66.9%. Let's call it 70 just for giggles. They diverged that the anchor and the test prefix took different paths. This says, whoops, somebody is not propagating the test prefix. So they took a different path. They found a less optimal path. In fact, it might have been less congested and be more optimal in some sense, but they didn't take the same path. The test prefix stops, but the anchor is okay. Oops, you can't get there from here. There were either multiple cuts or there was only one way to get there and that was cut. And then neither the anchor nor the test prefix could get there, and that was actually 4%. Okay? Either anchor or anchor and test field, right. Okay, so we derive the candidate links from multiples. In other words, hey, one got through from this way, one got through from that way, oh, it wasn't him, it was therefore she, 2 hops further on is more likely. And we get about 34 ASs that contain filters, and there's a wonderful list. And we'll like verification, and we've posted that to the internet, the NANOG list. The evaluation, why we like in probes? Well, trace routes go around the Bogon filters if there's an alternate path. They find a way to get there. Okay? And we get detailed information at the forwarding path, router by router. The disadvantages, we must find traceroute sites behind Bogon filters. And traceroute sites and people who read on the NANOG list and say, gosh, yes, I'll volunteer to help run your program for you. And Planet Lab nodes are not unbiased against distribution of clue. So therefore, these sites are more likely to be good than the victims, poor end users, sitting behind people with less clue. So these results are probably optimistic, but they give you a technique at least. Okay? And there's never enough traceroute sites because you really want the entire edge of the internet. That's large and is rumored to be growing. Okay. So the goal is to test as many ASs as possible for reachability. We'd like to know how well we're actually covering those edges. So the solution is outprobes. Outprobe, you ping and trace route from the test site to the edge. The return path is of interest. That's what you really would like to know. Can that site get to the test prefix? But you can't test that. So what we learn is which ASs out there have connectivity. I can reach them. And it works, it is good because it gives us high AS coverage, but it only tells us connectivity. It doesn't tell us optimality of path. Okay? By the way, feel free to interrupt if A, you find bugs, and B, I'm not being clear. So what we did is we went to the test sites and we went to all the ASs in the routing table. And we went and did scan pings to try and find a pingable scan pings from a source address that we thought was good. You know, an old anchor prefix, 147.28, whatever. And we sprayed out there cautiously and tried to find within every AS a pingable address. We didn't succeed, but we got 18,000 odd ASs. If the ping comes back, yes, that can be reached, which was 85% of ASs we were able to reach. If the ping does not come back, well, the anchor lick says, we don't know. So, approximately 2,500 ASs. We, depending upon which probe site we were coming from, we couldn't find something pingable there. Now, we did get email back from large corporations that announce a 24 and that's about it. And they said, why are you scanning r/24? And of course, what they've got is a firewall. They're using 2 addresses in that /24, and the rest of them are used for detecting evil people like researchers and sending them a nasty email. And so we responded in the usual way and told them that, sorry about that. You do notice it was a ping. So, we built a filtering likelihood index based on proximity and observations per AS if we had multiple pingables in the AS. Okay? And we said, this is the CDF of AS versus link. In other words, how much better information do we get if we look at links or ASs? Okay? It's significant in some of the ranges. Okay? No problem, I'll finish in 10 minutes. We derived 443 candidate ASs that are likely to filter. We then did a manual search for 15 and found 15 traceroute servers within those ASs. 7 of them clearly filtered. 5 did not filter themselves, but their upstream or side stream or whatever, in other words, their way to get towards us was the culprit. So now you're at 12 of 15, 80% were correctly identified. 3 failed, but we suspect some of that might be that we actually went and did this part of the validation after the measurements were taken. And, you know, there was only so long Aaron was holding on to that space and so long before people propagated their fixes, et cetera. We don't know. We do intend to do this again. Okay, so outprobe told us about reachability. Can we get there? And where you can get to and where you can't get to. They have much better coverage, but they don't really tell us about the return path, non-optimal paths, and where the diversion is happening. Whereas in-probes tell us about filters on the path, available reachability, much smaller coverage. Would love more tracer route servers, please. Okay, so we have the list of suspected Bogon filterings out there, and we've gotten some feedback, and yep, people said, ooh, sorry about that. And we said, thank you. We have an increasing number of in-probes. We're trying to get an increasing number of in-probes, in other words, sites from which to trace route, so we can detect better. How accurate can we be? There are some parameters we could change. How many test sites we have? Currently we have 4. The next cycle of this research, I, of course, came into this from the operational angle, and my co-workers came in it from the academic angle, and so the paper is going to be in Kyoto at the SIGCON conference, and then they'll be happy, and we'll get to work on actually deploying operationally. So we're going to be working with the RIRs for actual deployment. So the question is, how many probe sites do we actually have to put out there to be usable? If we put 5, is there a significant gain over 3? Okay. How do we quantify that accuracy? How do you say how accurate this is? Are we down to the router level? Are we down to the AS level? Will we settle for 20% error? People writing back and said, you said I was broken, but I'm not. I don't know. Good questions. Okay. From the outprobes, we can identify unreachable places. Okay. And aside from small issues related to ICMP and whether it's propagated and whether UDP ping versus ICMP ping, we know that if the probe doesn't come back, that they don't have connectivity for us. That's real simple and straightforward, but it doesn't tell us exactly where the problem was. Okay. Now, if we have the AS map, then you can never get a true AS map, but if we have a partial AS map, we can start, again, making conjecture about where it's broken between us. But it's possible to get good coverage without probes because you can ping towards the edge. And it produces some usable results. The in-probes, we can do further and actually start to really pinpoint. Okay, but we mainly look at trace routes that reach both the destination addresses. And of course, there's the problem of how many there are out there. Okay. We're trying to work with registries to fund an ongoing service, or not fund it, we don't want to do this for a living, but we're helping them establish it. We need more pingable addresses, we need more trace route servers, etc. Aaron gave us the IP space, they commissioned the research, etc., etc., as one of their chunks of ongoing research with which we participate. CityLink in New Zealand, Annie Linton, IIJ, SpaceNet, my site, University of Delft in Adelaide, and some people paid some money. Questions? Woo! You get away free? Come on.
Wow, thank you, Randy.